Long before anyone learned to pull iron out of the ground, humans were already working with it. They just didn't know where it had actually come from. The metal fell from the sky. For thousands of years, the only iron humans possessed wasn't mined, wasn't smelted, wasn't extracted through any deliberate process at all. It arrived on Earth already formed, inside meteorites, and ancient peoples simply picked it up off the ground like a strange, heavy stone that happened to hammer into shape better than anything else they'd ever touched. We don't know the exact moment humans first figured out how to make iron themselves, rather than waiting for it to fall from space. But a remarkable recent archaeological study gives us one of the strongest clues yet about how that accident may have happened. The story begins in a cemetery on the banks of the Nile, in a town called Gerzeh, roughly 70 kilometers south of modern Cairo. In 1911, archaeologists excavating burials there uncovered 9 small tube-shaped beads strung together with gold and semi-precious stones like carnelian and lapis lazuli. At the time, nobody thought much of them. It was only decades later, when researchers began analyzing the metal itself, that the beads revealed something extraordinary. The beads dated to somewhere between 3600 and 3350 BCE, more than 5,000 years ago, making them among the oldest known worked iron artifacts anywhere on Earth, and they predated any known evidence of iron smelting in Egypt by well over 2,000 years. For decades, that gap posed a genuine mystery. How had Egyptians been working with iron millennia before anyone in the region had figured out how to smelt it from ore? Early chemical testing in 1928 found the beads carried unusually high nickel content, a telltale signature of iron-nickel meteorites rather than terrestrial iron ore, which almost never contains nickel in comparable amounts. But the finding wasn't universally accepted. In the 1980s, some researchers argued the beads might instead be evidence of very early accidental smelting, muddying the picture for decades. The question was only conclusively settled in 2013, when a team from the Open University and the University of Manchester, led by meteorite scientist Diane Johnson, ran a far more sophisticated analysis using scanning electron microscopy and computed tomography to examine one of the beads without damaging it. What they found removed all doubt. The metal displayed something called a Widmanstätten pattern, a distinctive crystalline structure that only forms when iron-nickel alloy cools extremely slowly over millions of years inside the core of an asteroid, something no furnace on Earth could ever replicate. The scans also revealed exactly how the bead had been made, not melted or poured, but cold hammered, a fragment of meteorite beaten patiently into a thin sheet, then curled into a tube. No smelting involved at all, accidental or otherwise. Ancient Egyptian metal workers had taken a rock that fell from space and, with nothing but patience and a hammer, turned it into jewelry. They weren't alone in doing this. More than 1,000 years after the Gerzeh beads were buried, meteoric iron turned up again in one of the most famous tombs in history. When Tutankhamun's burial chamber was opened, among the treasures sealed inside was an exquisitely polished iron dagger, along with an iron bracelet and headrest. For decades after their discovery, some archaeologists speculated that these objects proved ancient Egyptians had achieved a significant mastery of iron smelting centuries before the Iron Age officially began. Metallurgical analysis in the 1960s, later confirmed with modern techniques in 2016, put that theory to rest. Tutankhamun's dagger, like the Gerzeh beads more than 1,000 years earlier, was made from meteoric iron too. And the story goes further than Egypt. A more recent study, using portable X-ray fluorescence spectrometers to test Bronze Age iron artifacts from Syria, Turkey, and Egypt without damaging them, found that objects long assumed to represent early experimental smelting were, once again, meteoric. The study's own conclusion was blunt. Speculation about early Bronze Age smelting needed to be revised. As recently as a few years ago, researchers were still confidently correcting the historical record, discovering that supposedly smelted ancient iron kept turning out to be, quite literally, out of this world. It's worth sitting with how strange this actually is. For thousands of years, one of the rarest, most prized substances available to some of history's most advanced civilizations wasn't something anyone on Earth knew how to make. It was pure luck, quite literally, a matter of whether a chunk of usable metal happened to survive its fall through the atmosphere and land somewhere a human being might eventually stumble across it. Iron, before it was ever mined, was treated the way we might treat a fragment of the moon today, a rare rare, almost sacred material worth more than gold because nobody had any idea how to make more of it on demand. Here's the strange part of this story that trips a lot of people up. Iron isn't actually rare on Earth. It's the most abundant element in the planet by mass, forming the core of the Earth itself, and it's common in ordinary rock and soil almost everywhere humans have ever lived. If it's so plentiful, why did it take civilizations that had already mastered bronze thousands of years to figure out how to use the iron sitting right under their feet? The answer comes down to a brutal difference in the chemistry and physics involved. Bronze, an alloy of copper and tin, has a relatively low melting point, and copper ore is comparatively easy to reduce into usable metal. You can genuinely melt copper and bronze in a simple pot held over an ordinary fire, pour it into a mold, and produce a usable tool or weapon with equipment barely more sophisticated than a campfire. Iron ore is an entirely different challenge. Pure iron doesn't melt until temperatures reach roughly 1,538 degrees Celsius, far beyond what any ancient open fire or even most early furnaces could reliably sustain. Extracting usable iron from ore demanded not just heat, but an entirely different kind of specialized furnace, more fuel, more sustained airflow, and metalworking knowledge nobody in the Bronze Age world had any obvious reason to go looking for, especially while bronze was already working perfectly well for their needs. For a long time, historians assumed someone, somewhere, must have deliberately set out to solve the iron problem, methodically experimenting with hotter furnaces until they cracked the puzzle on purpose. A striking piece of recent archaeological research, published in September 2025, offers a very different, far more accidental possibility. At a site called Bolnisi in the country of Georgia, in the Caucasus region, archaeologists in the 1950s discovered the remains of an ancient furnace, roughly 3,000 years old, along with piles of a reddish mineral called hematite, iron oxide, and a glassy waste byproduct called slag. At the time, researchers assumed they'd found early evidence of intentional iron smelting. A 2025 reanalysis of the site, led by researchers at Cranfield University and published in the Journal of Archaeological Science, overturned that assumption, and in doing so, revealed something genuinely fascinating. The workshop at Bolnisi wasn't smelting iron at all. It was smelting copper. Ancient metalworkers there had been deliberately adding hematite to their copper smelting furnaces as what's called a flux, a substance mixed into a furnace specifically to help separate valuable metal from unwanted rock and impurities more efficiently, boosting the amount of usable copper they could extract from each batch of ore. Here's where the researchers were careful, and it's worth being just as careful repeating it. The study doesn't claim this exact furnace produced usable iron metal, or that this was the definitive moment iron was discovered. What the researchers argue is something more measured and arguably more interesting. Under the right furnace conditions, that kind of experimentation could have brought iron-bearing material into an environment capable of reducing iron oxides to metal. They propose this kind of copper flux experimentation may have been one of the crucial steps that eventually led metalworkers toward deliberate iron production, a plausible pathway, rather than a captured, confirmed moment of discovery. It's a strikingly ordinary origin story for a technology that would go on to reshape the entire ancient world if the theory holds up. Nobody necessarily set out looking for a stronger, cheaper metal to replace bronze. Somebody, quite possibly, was just trying to get slightly more copper out of their furnace using a mineral that happened to be lying around, and in doing so may have stumbled toward the first steps of an entirely new material. An accidental smear of iron inside a copper furnace, if that's really what happened, is a long way from a blacksmith deliberately forging a sword. Turning that kind of early exposure into something civilizations could actually rely on took centuries of further trial and error. Among the cultures of Bronze Age Anatolia, in what's now Turkey, the Hittites became closely associated with early, deliberate ironworking, with evidence suggesting real command of the process by the height of their empire between roughly 1500 and 1177 BCE, although the exact origins of iron smelting and exactly who developed it first remain genuinely debated among historians and archaeologists. Working around iron's brutally high melting point required real ingenuity. Metalworkers of the era layered iron ore together with charcoal inside shallow hearths, and rather than trying to fully melt the metal the way bronze workers melted their alloy, used sustained intense heat over many hours to chemically strip oxygen out of the ore, leaving behind a spongy, impure lump of solid iron known as a bloom. That bloom then had to be repeatedly reheated and hammered, driving out slag and impurities, gradually consolidating it into workable wrought iron. In some cases, ancient smiths appear to have discovered, likely again partly by accident, that iron absorbing small amounts of carbon from the surrounding charcoal during this process became measurably harder and easier to work. An early informal form of what we'd now recognize as steelmaking formed through carburization, a process that also happens to lower iron's effective melting point by several hundred degrees, making the entire endeavor slightly more achievable with ancient furnace technology. Here's a detail that surprises a lot of people. Even after some cultures had genuinely learned to smelt iron, most of the ancient world kept using bronze for centuries afterward. Iron didn't immediately replace bronze because it was simply better. Early wrought iron wasn't necessarily much harder than well-made bronze, and it demanded specialized furnace technology and far more fuel and labor to produce, while bronze could still be melted in a simple pot over an open fire by any metalworker who already had the skills. For a civilization already equipped with functioning bronze production, there was little obvious incentive to tear up a working system in favor of a harder, more expensive, more technically demanding alternative. Iron eventually won out, not because it started out better, but because people gradually learned how to make it better, and because iron ore was far more widely available almost everywhere than the tin bronze depended on. That second point turned out to matter enormously. Bronze depends on tin, and ancient tin sources were scarce and often located extraordinarily far from where bronze was actually being produced, forcing ancient economies to depend on long, fragile trade networks stretching across enormous distances to keep bronze production running at all. Historians studying the period have called the ancient tin supply chain one of the great unsolved mysteries of Bronze Age archaeology, a resource whose origins and trade routes remain only partially understood even today. Around 1200 BCE, much of that interconnected trading world came under serious strain. In what's now known as the Bronze Age collapse, a wave of political upheaval, invasions, and cascading economic disruption tore through the eastern Mediterranean and Near East within the span of a few decades, destroying major cities and severing long-distance trade routes across the region. Historians don't treat this as a single simple cause and effect story where tin disappeared and everyone switched to iron overnight. The transition played out differently, region by region and technology by technology. But one of the forces that clearly helped accelerate the shift was the disruption of those Bronze Age trade networks, tin among them, at exactly the moment iron-working knowledge, however it had first emerged, was mature enough to fill the gap. Iron, requiring no imported tin at all, just locally available ore, charcoal, and a proper furnace, went from curiosity to necessity across a wide stretch of the ancient world. That transition is what historians now mark as the beginning of the Iron Age, conventionally dated to around 1200 BCE. Within roughly 500 years, iron tools and weapons had spread across much of the Eurasian landmass, reaching India, China, and, evidence suggests, parts of Central Africa independently around the same broad period. The consequences went far beyond swords and armor. Because iron ore was so much more abundant and widely distributed than tin or even copper, iron tools became dramatically cheaper and more accessible than bronze ever had been, putting durable metal tools into the hands of ordinary farmers for the first time in history, not just elite warriors and craftsmen. In regions across India and China, iron plows and agricultural tools measurably increased farming efficiency, contributing directly to sharp, sustained population growth in exactly the areas where iron technology took hold earliest and spread fastest. That growth came with real costs. Iron smelting is enormously fuel-hungry, consuming vast quantities of charcoal, which meant vast quantities of wood. Historians studying Iron Age societies have documented significant deforestation linked to the demands of iron production and the expanded agriculture it enabled, one of the earliest clear examples in human history of a new technology reshaping the natural landscape at scale. Step back across this entire story and a striking pattern emerges, even accounting for exactly how much of it remains genuinely uncertain. At almost every stage, the discovery of usable iron looks less like deliberate, forward-looking invention civilization, and more like accident layered on top of accident, spread across thousands of years. The very first iron humans ever used didn't come from any human effort at all. It fell out of the sky, and ancient civilizations simply learned to recognize and shape whatever scraps happened to land somewhere they could find them. When true terrestrial iron finally emerged, the best current evidence suggests it likely wasn't because someone set out looking for a better metal than bronze. It may have emerged from metalworkers trying to extract a little more copper out of their furnace, using iron oxide as a simple additive, and inadvertently opening a door toward an entirely new material. Even after that early exposure was eventually refined into real metallurgical skill, iron only became the dominant metal of the ancient world once a fragile international tin trading network came under serious strain, leaving metalworkers leaning harder on the alternative sitting under their feet the entire time. The next time you pick up something made of iron or steel, a knife, a nail, the frame of the building around you, it's worth remembering that the entire foundation of that material's presence in your life may trace back not to careful planning, but to a chain of ancient accidents: a rock from space, a furnace additive that did more than anyone expected, and a trading world nobody saw collapsing until it already had. This may be one of the clues to how humans eventually discovered iron smelting, not the confirmed final answer, but a real physical trace of the kind of ordinary half-accidental tinkering that likely got them there.